Okay, all right, let's get to it. So we are going to finish 10.5 today. We're going to talk about planes. We'll have to finish the last example that I was talking about lines, but we'll also finish planes. How's the quiz?
Loved it.
Awesome. Okay, so there was one real problem on the quiz. The rest were just the formulas, regurgitating the formulas again. I assumed that the most difficult problem was finding the distance between the two lines. Were you guys okay with everything else?
No. You would go over that question because I left it.
You left the whole thing blank or just that one part?
Just part B.
The distance between the two lines. So there are three situations, distance between lines. And of course, when we say distance between lines, we mean the shortest distance between two lines. There are three cases. There's the case where they intersect, right? So the two lines actually pass through as common points. So what's the distance between them? 0. So that's the stupid case, right? So here the distance equals 0. Okay, there's also the case where they're actually parallel, right? So we have two lines that are parallel. And I gave you the equations of these lines. So assuming we know the equations of these lines and we want to find the distance between them, how do you think we'd go about it? Ideas?
Find the distance of the vector orthogonal to both.
Right, so what would that be? How would we go about that?
Find the direction vector both of the lines and then cross product them.
Okay, so we have this guy. So you want to call him something A and B? Okay, and you're going to cross product them?
No, I'm saying first have to find like the direction vector for both of the lines.
Yeah, assume we have those because you have the equations.
Yeah,
So you know
okay,
the
so
direction.
you know that.
So we know what A is, we know what B is. But the direction vectors actually be the same.
Between the vectors. Can you find the distance between the direction vectors? And that's it?
How would you know what the distance between the direction vectors? That's the whole point. What's the distance between these?
Pick a point on one of these lines and then generate the vector equation.
So I pick a point here and then do what?
And then generate the vector equation using the cross product vector.
With how?
0. Take a cross product of two parallel lines, 0.
Right, but clearly the distance is not 0. So
Find a normal vector.
sure, we can get a vector that's perpendicular. How do we make it work? So fine, let's say we get a vector that's perpendicular. How do I know I want to measure from this point to that point?
Do the scalar projection, pick a point, you have a point on B already, pick a point on A.
Okay,
Say that's P and Q, you've got a vector PQ,
so create a vector here.
and then scalar projection use PQ onto the perpendicular.
Okay.
I
Yeah.
don't know if I'm right on. Like, you have a vector A and then B, so you find the distance between two vectors.
How do you do that?
Like-
There's no concept of distance between two vectors because
No, like-
vectors are, you can move them around. Vectors aren't stationary.
But since they're parallel, right? They will.
I'm not sure. Would you have to parallelogram?
It's easier. It's pretty much the same method as finding the distance between a point and a line. Basically what you do is you create another vector C and you pretend, oh, what if I knew this angle between them? And then the magnitude of this would be the magnitude of C sine theta. Right? And so basically your distance is going to be C sine theta, which we can write as
Would you sign the 90 to find the shortest distance between two parallel vectors?
come again?
Wouldn't the angle have to be 90 to find the shortest?
This angle is 90.
And now you said it's
This is the angle I'm talking about here. I pick two random points on each line.
Oh.
Connect those with a vector. Consider the angle here. I can find the magnitude of this based on that angle,
Oh.
which I can then rewrite as this, which is just C cross B over B, right? So basically, you find a vector connecting the two lines, you cross product that with the direction vector of one of the vectors, divide by the magnitude of that vector. And that will actually give you the distance between the two lines. There's also the third case where there's skew, right? So these lines aren't touching, they're just skewed. So we'd want to be able to do the same thing here. The problem is, these lines are parallel, so if I found a line perpendicular to one, it's automatically perpendicular to the other, so we didn't have to worry about it. If I want to do the same thing here though, I want to connect this to that with the shortest distance. I would need a line that's perpendicular to this as well as it's perpendicular to that at the same time, right? That's how I guarantee the shortest distance. So how you would find that, so if I know this is A and that is B, I can find this vector by just taking A cross B, right? Now they're non-parallel anymore, right, because they're skewed. So what do you think? I can call this, let me call that N for now. So given that I can find that vector, how do you think we should proceed? As I gave you the hint, now is where you actually do a projection. So again, you pick a random point here and here, create that vector, let's call it C, and I'm going to project that vector onto this. And so basically the distance here would be the component of C onto N, which is just going to be N dot C divided by C. So in one case the distance is 0. In the second case you need a cross product in your formula. In the third case you need a cross product, but once you get the cross product you actually have to put it in a dot product. You use a scalar projection in this situation and you use trigonometry in this situation. That was basically it. Let's go back to...
Just have one question.
Yes.
When you create vector C, you do that by picking...
Any two random points, doesn't matter. So I plug in scalar t equals 0 here, scalar k equals 0 there. Just find any random points. Connect them with a vector, project onto the normal vector. The vector that's orthogonal to both. So we were talking about an example where we determined if the pair of lines are parallel, intersecting, or skew. We did the parallel example, right? And we did the intersecting example.
Yeah.
We completed the intersecting example.
Yeah, point is 2, 3, 1.
2, 3, 1. Okay, so
Sorry, I have a question about that.
yes.
Could we also do, so once you have the vector n, could you find where n intersects A and B and find the distance between those 2 points?
N would be a vector though.
Yeah, so the vector intersects another vector, so you can find that point.
Again, vectors intersecting vectors or distance between vectors is not really a concrete
No, but you know
concept.
that
If you want to follow your idea, you'd have to create a line that has direction vector n, and then you have to find a line that intersects with this and that,
Which is what you
which
did.
the arithmetic is going to be crazy. It's not impossible, but you have a bunch of systems of equations. As opposed to here, you can simply just dot product vectors. There are other ways to do this, by the way, which when we get to chapter 11, and we start to do things like critical points, you can actually describe the distance between these in terms of equations, but there'll be multivariable equations and you have to find the minimum distance. You can actually do it that way, but that is beyond our scope at the moment. We need chapter 11 for that. Anyway, so there's the last example. So we're continuing with 10.5. Example C, L1. 2. Well, that's what we're going to figure out. So here you can see our direction vectors are what? What's the direction vector for the first one and the second one? 3, negative 1, 1 for the second. Okay, so from this we can see that, are they parallel? Not parallel, right? One is not a multiple of the other. So we know it's not parallel. So now we're going to check, do they intersect? So basically when they intersect is when all the coordinates coincide at the same time, right? So the x coordinate has to coincide with the y coordinate, has to coincide with the z coordinate, and this all has to happen at the same time. Which means that this has to be equal to that, this has to be equal to that, this has to be equal to that. And you can set up a system of equations. So we need 3t to be equal to 1 plus 4k. We also need 2 minus t to be equal to k minus 2. We also need t minus 1 to be equal to minus 3 minus 3k. So I have a system of 3 equations and 2 unknowns. And remember how the trick we did here, you just solve for 2 of them and check whether or not it works in the third, and that will give you the answer. So let's look at equation 1 and 2. So equation 1 says 3t minus 4k equals 1. Equation 2 says k plus t is equal to 4. T plus k equals 4. That's equation 2. How do you proceed? Algebra.
Multiply the bottom by 4.
Okay, so you can multiply this by 4. 4. This will become 16. This is equation 2 times 4. So I can add those. The k's would die. I would have 7t equals 17, right? And so t would be 17 over 7. Okay, so far? Okay, so t is 17 over 7. What does that mean for k? So now we know since t plus k equals 4, right? We had that. So we will have 17 over 7 plus k must give us 4. This means k is 4 minus 17 over 7, which is going to be what?
11 over 7.
Now what? So we know t must be 17 over 7 and k must be 11 over 7. So now you check in the third equation. The third equation asserts that t minus 1 is equal to minus 3 minus 3k, right? Now if that works out, they actually intersect, and they intersect whenever our scalars have these values. So I can plug in here, t was 17 over 7 minus 1, right? So that would actually give us what? This is 7 over 7, so this is 10 over 7, right? This side would give us what? Minus 3 minus 3 times this, 33 over 7, right? This is obviously going to give us a negative number, right? So it doesn't work. Therefore, So on the quiz, if I didn't tell you that the lines were skewed, you had to go through all of this and check it, because remember, there are 3 different situations that you could have. Knowing the lines are skewed tells you that you want to try the 3rd situation, where you do that scalar projection. But yeah, that's it. It's a pretty typical problem to be put on a final. Figuring out whether they'll give you 2 random lines and ask you, do they intersect, are they parallel, or are they skewed? So the first thing you'll check is the direction vectors. And if they're parallel, you're done, right? They're parallel if one is just, if they're proportional, which means one is just a multiple of the other. You can see here right away from the 2nd coordinate that to go from 1 to a -1, this guy should be the negative of this one, but it's not. Right? So we know it's not parallel. Then you try to set up these equations and see if they have a solution. If it actually has a solution, then they actually intersect. If they don't have a solution, then you know they're skewed. They will never touch, but they're still parallel. They're not parallel. That couldn't happen in 2 dimensions, but in 3 dimensions it can happen. Any questions?
Actually, no. I think I understand. I was confused for a second why we had 4t plus 4k was 16 for the second.
Oh yeah, I just took this and multiplied it by 4 so that I can make these the same numerator, so that they cancel. Okay, let's make our lives more interesting. We're going to talk about planes. Because all the problems I can give you with lines are too easy. Okay, so now let's talk about how would we figure out the equation of a plane? How do we know what a plane looks like? It turns out, just like a line, to figure out the equation of a plane, we're going to need a point and a direction vector. Now for a line, we needed a vector that's parallel to the line, but could that work for a plane? Couldn't work for a plane, right? So a plane is just like a flat sheet of paper, right? Just like this, right? Now let's say I have a vector that's parallel to this plane, right? Is that unique? Well, no, because this plane is also parallel to that same vector, right? That plane is also parallel to that same vector. Knowing the parallel vector gives me nothing. There are an infinite number of planes that are parallel to this one vector, right? What happens though, what if I knew a vector that was orthogonal to the plane? How many planes do that? Only this one, right? Because as soon as I start to tilt this guy, it's not orthogonal anymore, right? So if I know a vector that's orthogonal to the plane, I can uniquely identify the plane once I know a point it passes through. Because there will be only one plane that is orthogonal to this that passes through a given point. Right? So to find so with that discussion, we know we need a point in the plane and an orthogonal vector. This orthogonal vector we call the normal vector. What do we need to find the equation of a line? A point and a direction. What direction? Direction parallel to the line. What do we need for a plane? A point and the normal vector, right? Make sure you know this, right? So if you're looking for the equation of a line, you need a point and a direction parallel to the line. You're looking for a plane, you need a point and a direction orthogonal to the line. Now, assuming we can find these, how do we write down the equation? By the way, how do we know if 2 vectors are orthogonal? You guys are taking too long. Too long vacation. Okay. All right, moving on. So let's say we have this plane here. And I actually know a normal vector. So I figured out a vector that's orthogonal to this plane. And let's say I know a point in this plane. X0, Y0, Z0. And let's assume we know what point that this vector hits the plane in, if it's a line. And let's call that X, Y, Z. This is a general point, right? So this is a specific point that I know is in the plane, right? X0, Y0, Z0. This is a general random point that I'm going to try to find the equation that relates X, Y, and Z. At that point, I base a normal vector. Notice that I can create a vector here, right? So let's say I create this vector, call it, it doesn't matter what we call it B. How would I know that B is orthogonal to N? Dot product is, I just asked you guys that like 30 seconds ago. This must be true, right? So this, I know 2 points in the plane, so if I create a vector with those two, I find a vector that's parallel to the plane. If the normal is orthogonal to the plane, it must be orthogonal to this vector, which means the dot product is 0. So, which means, let's say I know the components of this normal vector, call it A, B, C. This would mean x minus x0, y minus y0, z minus z0, dot product A, B, C should give us 0. Which means if I take this dot product, let me write it down. That relationship must be true. That is the equation of a plane. And that is also the answer to one of the bonus problems on the quiz. So when I ask you what the equation of a plane, you were supposed to write down this. When I ask you the point, you were supposed to write down that. And the normal vector, you were supposed to write down ABC. So if we know a normal vector, a vector that's orthogonal to the plane, components ABC, and we know a point, we simply plug them into this formula. That's the equation for your plane. Did you have a question?
Yeah, I was asking, I didn't say the vector equation, so I just put the linear equation on the x plus by plus cz plus a plus 0.
No, you asked that thing.
Huh?
You asked something.
Well, the vector equation of the plane, it would be this, but you very rarely write that like that. You'd set it that way. Did you write this?
No.
Okay. Did you write that?
No, I wrote the linear.
Okay, doesn't matter. Because if you write the, what did you say you wrote?
Ax plus by plus cz plus a equals 0.
And how do you know a point that passes through that plane?
I just put x0 and y0.
But it wasn't in your formula, so it doesn't match. Okay. Yes, you could also write this in the form ax plus by plus cz equals some constant d. But this, when you write it in that form, you lose the point, right? So after you get this, you can simplify to that, but when you're first figuring out the formula, that's the guy you want to use. Okay, let's do a couple examples. Well, I'll wait for that coffee to kick in. Okay, finding prudent. Start out simple. Equation of the plane that passes through the point 1, comma 2, comma 3 with normal vector minus 1, 7, 4. Find the equation of the plane. Continue. I'll give you 3 points on this plane. 1, 2, 3. 3, 2, 1. And minus 1, minus 2, 2. Okay, how do you do this one?
Plug into the formula.
What would it be?
Negative 1, parentheses x minus 1, plus, parentheses 1 minus 2.
7.
No, sorry, 7, 1 minus 2. Plus 4, parentheses 2 minus 2. 2, 0.
Yep, that's it. I wouldn't expect you to expand and simplify that. Giving me that as the answer is completely fine. That's it. So all you have to do is realize that this is your A, B, C. This is your X naught, Y naught, Z naught. Plug into the formula. So if you know a point and you know the normal vector, plug and chug. That's pretty much it. This really has nothing to do there. Second problem is a little more involved. How do we do that? Right, so to find the equation of the plane, we need the point and the normal vector. Here I know 3 points. So I definitely have the point down, right? I can find a point, no problem. How do we find the normal vector?
Points QR, and the vectors PQ, QR, and then take the cross product of the two.
Exactly. So here's a plane. I know that there are 3 points in this plane. I have 1, 2, 3. I have 3, 2, 1. And I have minus 1, minus 2, 2. I need to get a normal vector. And John said it. Create 2 vectors. These both vectors will be parallel to the plane because they're connecting points in the plane. And if you want a normal vector, you need that vector to be perpendicular to both of these. You need to go orthogonal to both. So your n is going to be, if you call this vector A, call that vector B, then n is going to be equal to A cross B. Well, technically it's minus A cross B, but who cares? All right? A cross B, that's good enough. So that's what we're going to do. So here we know that A is the vector, what's the vector A? 2, -4, -1, vector B,
2,
Gonna take the cross product here. Right, so your I, J, K, and so your N is going to be the vector, what's it gonna be? 8, right? Middle. We have 4 plus 2, right, which gives us 6, but when we take the negative, cover this up, 0 plus 8. So we have that as our normal vector. We could scale this. It's equivalent to using 4 minus 3, 4. Do you have a question?
No, I just wanted to make sure. I thought it was the dot product because when you were explaining planes, you wrote E dot M. Are we really doing the cross product with this one? Just want to know because I wrote down something else. Is it the cross product or dot product?
For this problem,
Yeah, for this problem.
it's definitely the cross product that we want.
I was saying in the notes earlier you said that you had to cross B and N to get 0, but then the way to find N you had to cross product it.
No, you have to dot product B and N to get the formula.
Yeah.
Because the dot product of N with B or N with A will be 0.
Okay.
But that gives us a scalar. Dot product gives us scalars.
Right.
What I need is a vector, so I wouldn't use a dot product.
Okay.
Right?
Right.
So it comes down to knowing what each guy gives you and figuring out what you want. I want a vector that's orthogonal to both. How do we find that? The cross product. So I can use that. So this means, what's the equation of my plane? 4 times. Pick a random point. Let's say I pick the first one, x0, y0, z0. It doesn't matter which one I pick actually. When you simplify, they'll all be the same. 3y minus 2 plus 4 z minus 3 equals 0. That will be the equation of the plane. I wrote down what that simplifies to. This, by the way, simplifies to 4x minus 3y plus 4z equals 10. Right? And you'll see, if I pick any other point, if I didn't choose 1, 2, 3, or I chose this or I chose that, you'd realize they'd all simplify to this. Right? So it's not something you have to worry about.
If you have 3 points, they have to make a plane, right? If you can't have 3 points that can't be on the same plane.
It depends on your direction. So the thing is, given any 3 points, any 3 distinct points, I can find a plane that passes through all 3. However, not any 3 points would lie on a particular plane that I'm given. So it depends on what
But
direction.
4 points, you're given 4 points, they're not necessarily the same plane, right?
Right. So 4 points, it doesn't have to be a plane with 4 points. But with 3 points, you can always find a plane. Okay, what else do I want to talk about? Let's talk about distance. We often need to find the distance of things. Let's say to a plane that I can write as ax plus by plus cz plus d plus e plus 0. So want to figure out a formula for this. Just going to show you how it's done. So let's say here I have a point P, which is x1, y1, z1. A random point in this plane, based out at x0, y0, z0. And I have a normal vector hitting this point. How do I figure out the length of this? Scalar projection of what?
X naught, Y naught, Z naught, the vector connecting that point to the point P.
Right. connect these with a vector, call that b, and then the distance would just be the scalar projection of b onto n. Which, by the way, if you write that out in the formulas, I'll have to write it down here. So b would actually be x1 minus x0, comma, y1 minus y0, comma, z1 minus z0, dot product with n, which I'm going to call ABC, because that's how I defined it, divided by the magnitude of the normal ABC. That's by the scalar projection. So this would actually give us ax1 plus by1 plus cz1 all over the radical. That gives us a distance formula from a point to a plane. Okay, what else do we want to talk about? Now you gave an example after that. As you can see, projections are pretty useful things. You use them to find equations of stuff, come up with distance formulas, find the distance between 2, 8, 4, and 2x plus y plus 3 equals 5. Oh, sorry, I'm missing the b here. Plus 3. So what's d? The distance. Probably shouldn't put it. Or this is capital D. To not mix up with that d over
Where
here.
did that smaller d come from?
Where do you go from?
If you expand this, you'll eventually get a times x naught plus b times y naught plus c times z naught, which we know lies on the plane, so it must equal minus d. And if you write out the formula, you'll see it. It's pretty much that we did something similar to this in 10.3, right? The distance from the point to a line, remember, it was pretty much the exact same derivation. So if you actually multiply these out, you'll see that the d gets substituted because it's in the equation of a plane. What about here? What's the distance?
Actual value of 2 times 2
2 times 2
plus 1 times 8
plus 1 times 8
plus 1 times 4
plus 1 times 4
minus 5
minus 5 divided by
4 plus 1 plus 1 square root.
That's it. And what does that simplify to? Here, 11 radical 6 over 6. Do you feel like rationalizing? It's pretty much all I want to do in this section. Those are some simple examples just to get you used to the idea of finding planes. In the homework, you'll have a lot more interesting situations to figure out. For example, if I have a plane, suppose I have a plane, I know a line that's in the plane and a point that's in the plane. Could I find the equation of the plane from that? How? Huh? Pick a point on the line? Okay. Well, we wouldn't need a second point on the line because we know the equation of the line, right? So I tell you, this is the equation of the line, I know it's in the plane. So I automatically know what that vector is. So I wouldn't need a second point here. But I can create that new vector, cross product, get the normal, and continue that way.
So the equation of the line would come with a point in the vector?
Yeah, I'll tell you, this line is in the plane, this point is in the plane, find the equation of the plane.
Okay.
What about if I asked you, two planes intersect into a line, could you find the equation of the line? So I have could you find the equation of that line?
Yeah.
If I give you the equation of the two planes, can you figure out what that line is? How?
Just make equal to each other.
How would you make them equal to each other? How would you make them equal to each other?
The direction would be going back and cross product to the normal vectors.
Why would you think of that?
Yeah. The normal vectors would be orthogonal. They both be orthogonal to the thing that they're both parallel to.
They both are orthogonal to the thing they're orthogonal to? Well, that's true.
Just pick 2 points.
Yeah, you can figure out the direction of this guy by actually cross-producting the normals. So you take the normal of one plane, cross-product the normal of the second. Why? Because if this line is an intersection, it means it's in both planes, right? Which means it's parallel to both planes. Which means it's perpendicular to both normals. Hence, it's given by a cross product, right? How would I figure out a point? So this would give us the direction, but I need a point as well. How would I figure out a point that's in both planes?
Find the point when the x, y, or z are equal.
Sure, we need a point where the x, y, and z are equal for both. How do we get to that?
Right? Set them equal to each other and solve.
What do you mean set them equal to each other?
Get to equations.
So let's say one plane is 4x minus 3y plus 2z equals 5. The other one is x plus 2y minus z equals 6. What do you mean set them equal to each
Can
other?
we give you those equations?
Yeah, I give you these equations. And I can find the direction of the line by just taking 4 minus 3, 2, cross-producting with 1, 2, minus 1. That gives me the direction. How do I find a point?
If you move the d's back on the other side so they would equal 0 and set them equal to each other, then you could substitute different values for x, y, and z. That's what they.
Yeah, so basically, you only need to substitute 1. So for example, I can say, let's figure out what they intersect when x equals 0. I could just choose that, right? So I can figure out where do they intersect in the xy plane. Just make this guy 0. I have a system of 2 equations, 2 unknowns. I can find the other 2 points. Or I can make y equals 0 and find the other 2 points. Or I can make z equals 0, find the other 2 points, right? So if I let x equals 0, my point is going to be 0, something, something, which is good enough. Or if I let y equals 0, I would have something, 0, something, right? Or if I choose z equals 0, I would have something, something, 0, right? Any of these points would be in both planes at the same time, right, by solving simultaneously. What about... I could give you other examples, but I think the homework has a lot. So just think about those. So 10.5 is the first place where actually now we have to be doing some thinking about how things work in 3 dimensions and what's parallel and orthogonal, which is why you really need to know what a dot product gives you, what a cross product gives you, how to find distances, how to find points, how to find directions. It's all important. Do I want to start the next section?
No.
I don't. I don't. The next section is cool though. We're going to learn to graph stuff, like draw surfaces, cylinders and quadric surfaces.
As far as that sounds.
Anyway. Yeah, I'm not. I'm running on like an hour and a half sleep. So let's talk about something else though. You don't even have to take notes, so you can just listen if you want. So you can take it easy. So you'll notice something about your syllabus is that in Calculus 3 you'll see the syllabus and we start in the double-digit chapters. So we do chapter 10, then chapter 11, then chapter 12, and then chapter 8. Like what the hell is up with that, right? So it turns out that the way City College organizes the calculus sequence is different from other colleges. You do a lot of stuff in Calculus 2 here that you don't do in other colleges. So some things that they usually do in Calc 2, they do here. For example, chapter 8 is typically done in Calc 2 at most other colleges, right? But because we packed other stuff in Calc 2, it gets pushed to Calc 3, right? And there are a lot of things in 392 that other colleges do in Calc 3 that got pushed to 392. If you're an engineer, you'll see the whole spectrum, but yeah, you have to be aware that the organization is different. So that's why we do chapter 8 in Calculus 3. So one thing you should realize is that, well, you should realize that. So chapter 8 is a Calculus 2 topic, which means what? It should be easier, right? You should be like, oh, Calculus 3. So what happens though is, the reality of the situation is, professors usually spend so much time in the calculus chapters 10, 11, and 12, and what happens is, reach the end of the semester, you have like a week and a half left, and they're just like, oh, it's a Calculus 2 topic. And they rush through it lightning quick. Everyone's confused, everyone does horribly when it comes to chapter 8. But it's not something that you should do horribly on because it's a Calculus 2 topic. It just requires a different kind of thinking. And so I feel like a lot of students can't switch gears in their head. They're like used to doing all this calculus stuff and then now, series, you know? It's like you're flying down the highway at 70 miles an hour and then you're like, switch into second. Probably a bad idea. Bad example in America, you guys. You like automatic, I don't. How does it work with automatic? You're flying down in your automatic car and you put it in park on the highway, like 70 miles per hour, right? Like put it in park. Really bad, right? It's like, it should be easy being in park, but if you're flying at 70 miles an hour, it's not so easy trying to adjust to it, right? So if you're in a manual car, just take my word for it. Flying down, you know, you're in 6th gear and you're down the highway like 90 miles an hour, illegal. I'm not saying you should do this. And then you're like, boom, and you put it in 3rd gear. What's gonna happen? Something bad. The car's gonna like, right? It's going to slow down the car because the car can't manage the high speed at that gear. And so what happens is eventually the car will stabilize, but it's going to be a rough time. So what happens is you're doing chapter 3 and you're in chapter 10. Fourth gear, okay, chapter 11, fifth gear, sixth gear, you're in chapter 12, and you're like, yeah! And then I go chapter 8, boom, second gear. Now what happens is, you only have a week to adjust. It turns out that most people can't adjust in that time. So they're freaked out, they careen off the highway and they crash, right? By the time they hit the final, they're like, no, seriously, I'm just gonna skip this on the final, right? Turns out you can't really skip it though, because they usually put a series problem in the compulsory section. So, because it's sort of hard to switch gears, I thought what I would do this semester is try to introduce some concepts to you guys earlier. So I'll have like these blurbs on series at the end of a few of my lectures, where I just talk about series for a few minutes. So it sort of gets you used to the kind of thinking you'd want. So let's do that. So you don't have to take notes because we will be seeing this at the end of the semester when we're like rushing through at 6th gear and we're going to switch back. So what's going to happen is we're going to talk about series. 8.1 students usually don't have trouble with, that's sequences. But after that you will talk about series. So basically what's a series? Does anyone know? Anyone to talk to somewhere else?
Infinite number.
It's not necessarily infinite, it's a sum, right? Just a fancy word for a sum, right? So I can say 1 plus 2 plus 3, that's a series, right? And it's a general sum, so I can, subtraction also counts, so that's a series. You say this is a finite series, right? Has 3 terms in it, right? We can also have things like infinite series, where we're adding an infinite number of terms. 1 plus 2 plus 3 plus 4 plus, and you continue forever, right? So these are known as finite series. Finite series we can always find an answer for, right? So if I'm adding a finite series of numbers, I can actually figure out what the answer is, right? It might take some time if my series has like 100 terms in it, but we can find the answer. So the answer to this would be 6. Right? And the answer to this would be 2. And in fact, what's 9 plus 10?
19.
It's not 21. Okay, alright, you guys are probably too young for that one. Okay. Alright, so, right, it's 19. You can find the answer easy, but what if I said, okay, what does this one add up to? Can actually put a number on the right side of this thing. Yeah, does this add up to something?
No.
So some people watch number file, be like, minus 112. It's not really minus 112, don't worry about it. But no, you keep adding these and you keep going forever. Your numbers keep getting bigger and bigger, so what happens? We say this guy goes to infinity, right? We say the series diverges. Right? Or we can say, if we want to be particular, diverges to infinity. So you wouldn't have an answer for this series. Or what if I said something like 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. And I ask you, what does that add up to?
Alternating diverges.
It's alternating, diverges. Because the sum actually depends on where you stop. If I stop after the second term, it's 0. But if I go one more, it's 1. Then it's 0. Then it's 1. Then it's 0. Then it's 1. Then it's 0. Then it's 1. What is it going to add up to? Nothing. Right? This guy also diverges. It doesn't diverge to infinity though, but it does diverge. There is no answer to it. Right? I can't actually say this equals and write down a number. It wouldn't make any sense. Now some of you might be thinking, yeah, well, wouldn't that always happen? Turns out the answer is no. For example, 1 plus a half plus a quarter plus an eighth plus a 16th. Anyone knows what that adds up to? 2. It adds up to 2. And this goes on forever. It never stops, right? I'm literally just doubling the denominator, and I keep doing this forever. It turns out if I took an infinite number of numbers that follow this pattern and add them all up, 2 would actually be the answer. Like, this infinite sum is actually equal to a finite number, right? It's sort of a strange concept. Well, not that strange. You sort of encountered the same thing in Calc 2 when you were doing improper integrals, remember? And sometimes you had to like integrate from a point to infinity. And then sometimes the integral actually converged. Remember what that thing? Yeah, it's like you had this infinite area, but it's actually a finite area. You can actually add an infinite number of things and get a finite number, which is sort of strange. So finite series, no problem, right? Those you punch into your calculator. Infinite series, though, they can be a little tricky. And you might think all things that look like this would actually have an answer, but it turns out that that's actually not true either. So for example, if I had 1 plus a half, plus a third, plus a fourth, plus a fifth, it might look very similar to the one above, but it turns out that this one diverges to infinity. Okay. So yeah, we're taking fractions, doubling denominator. Here, denominator is still increasing, same thing. This one goes to infinity, that one actually adds up to something. Hence the study of infinite series. It's very important for us to know when a sum diverges from when it converges. Right? It will help us with more than I can explain in Calculus 3. Series are an insanely important topic when it comes to mathematics. One basic example of a series that you've seen before. Does anyone know? In calculus? Riemann sums, the integral, right? When you write this down, and you actually do an integral, and you do your little formula, the power rule and blah, 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 what you're actually doing is an infinite sum. Remember, this was actually defined as a Riemann sum, right? This was f of xi times delta x, where your I went from 1 up to infinity. An integral is an infinite sum. When you can integrate something and you get a formula for it, what it means is you can add up an infinite number of things and actually get a number at the end. Right? Now, if your integral doesn't exist, like you can't find it, it means your infinite number of things diverges to infinity or doesn't give you an answer. Right? So something like an integral is a very simple example of an infinite sum where it's actually super important for us to know what the answer is because we know all the applications of integrals, right? You wouldn't have engineering without integrals. You wouldn't have calculus without integrals. It's half of calculus is the integral, right? So many applications of an integral you will not believe and you will not fully appreciate until like the end of your engineering career. When you look back at all your courses, you're like, holy crap, did a lot of integrating, right? Like almost everything you'll be doing, right? A lot of your engineering classes will feel like math classes. A lot of it has to do with integrals. And far more sophisticated integrals than this one. We're going to be doing more sophisticated integrals as well. But the idea is being able to evaluate a sum, an infinite sum, is going to be very important for us to know. When does it diverge? When does it converge? This is called convergence. You say it converges to 2. So chapter 8 basically is the study of sums. There are a bunch of situations where we can actually know whether it diverges or not. And there are a few situations where we can actually tell you what the answer is. I can tell you what the answer is here because this is a geometric series. It's a very well-known series we'll talk about. I won't go to chapter 8. This is a very well-known series also. It's called a harmonic series. It's well known that it diverges. Right? And basically what we'll be doing in series is studying things like these. Studying infinite sums. We'll use sums that we can find a formula for. So for example, 1 plus 2 plus 3 plus, I could actually write this as something like n goes from 1 to infinity of the number n, right? So a lot of times I can write a series in a shortened form, which I'm going to remind you about this, how this form works. But yeah, if I can describe a sum in terms of a formula, there are tons of things I can do to figure out, does it give me an answer or does it diverge? And we're going to do a bunch of tests. I don't remember if I put it in your syllabus. Did I put a table like this in the syllabus or no?
I don't think so.
Okay. Yeah, well, I'll be handing this out when we do series then. Don't worry about it if you don't have it. I thought I put it as a supplement to the syllabus, but whatever. When we're covering series, I'll give you that table. So it's going to be a table of very well-known series formulas where we can figure out whether it converges or diverges. Does the answer go to infinity or does it go to something else? Right? And it's going to feel very different from chapters 10, 11, and 12. And so it catches a lot of students off guard, and it makes it feel harder than it actually is. Series is the easiest topic in Calc 3, but because they rush through it at the end, it feels difficult. So I thought I'd just slowly start to introduce some ideas to you. Okay, this is sort of what it's all about, being able to add infinite things. Right? And we want to know when we get an answer from when we don't get an answer, because it's super important. For example, it will help us with things like integrals, which are super important. Right? And we will know when we should expect something to diverge or converge. So we're going to talk about different things you can look for. So for example, I can know if the limit of the terms do not go to 0, it will definitely diverge. Whereas if the limit does go to 0, you need more information, right? Little things like that we're going to talk about. We're going to be able to sort of emphasize certain properties of this sum to figure out what the answers are. So you notice that these guys, they don't have a limit. The numbers keep getting bigger and bigger. This guy, though, the limit of the terms will go to 0. They keep getting smaller and smaller. It might have an answer. However, there are cases when even that doesn't work. Right? The idea is they don't get small enough, quick enough. Right? These guys get smaller a lot faster than these guys. How do you know when that happens? Well, we'll talk about it in chapter 8. Right? So that's some very important things that we will be doing in chapter 8, which throughout the semester I'll be talking about it every now and then at the end of class to sort of get you know, so we avoid flying down the street and going back into second year. With that, we will end. So 10.5 is complete, so the homework for that is due tomorrow, and we will do 10.6.
And you want us to email you MATLAB or print it out?
Oh, the MATLAB just printed out. So publish it as HTML. So I'll see your code and the graphs below it. Just print it out. Make sure your name is on it and all that, and hand that in tomorrow.
I'll just figure those all out.
It's in the menu bar, like File, Publish. It'll be somewhere in there. Just Google it if you don't remember. I don't remember it off the top